Good afternoon. Today will be the last session of chapter 6, and today we have all the theory about the sewer design, and this is a quick review. We have the flow. We have to estimate the maximum flow, which is equal to the average multiplied by the peak factor. Here is the peak factor, either one of these two numbers. This will give you the maximum, or and the minimum one, which is will be by 20% of this P1 over 6, and will be the minimum. That will be when we have the flow, and when we have a dry weather flow, it means that we have to estimate just only the population. And when we have a wet weather flow, will be the maximum peak flow times the Q average plus the rainfall plus the infiltration, if we have that one. And we say that the main important point is to be the slope. And here's the velocity of the known velocity that we have, 0.6 and 1.5. This is called self-cleaning velocity, and this is to prevent the sewer erosion. And mainly, if it's not given to you, the slope line of the sewer, it will be 1 over d, and d here will be in millimeters. What's that means? It means that if we have a pipe of 250 millimeters diameter, will be the minimum slope. It will be 100 divided by 250. This will called as a slope, and this is the hydraulic slope, and we will consider it the slope of the sewer itself. And we have this equation, and this belongs to Manning. And for Manning, we have Manning coefficient. The Manning coefficient will be varied from 0.01 to 0.017. We usually use this one for plastics. And we have for concrete 0.013, and it will depend how much rough is the surface of the flow, if the surface of the material is there. So for concrete, we are using 0.013. For new plastic, we are using 0.01, and so on. We say that we have a hydraulic radius, which is equal to the area. And which area? The area that will be wetted means that the area that will be covered by the flow, and the P, which is the parameter of this one, and the hydraulic slope. This is what I told you, that we have it here in sewers, that we have, it should be greater than the minimum, which is 1 over d. D in millimeters. So this head, losses in the head divided by the length of the pipeline, and usually it will be less than 100 meters. So this edge, it should be that much, and it will be greater than 0.1.025. And here's what I mean by the wet. So if you have, this is a sewer, and this is the cross section of this pipe. So you can see that the flow will be here till now. So this is called the depth of the flow. This is small d, and there is a capital D, which is the diameter of this flow. So we say that d over d will represent how much is the fullness of this flow. So if I have d over d have a 100%, that means we have a 40 flow, which is not accepted in the sewer design. It should be less than the 100%. And if we have 50%, it means that this is a half flow. And there is an area when it is a flow like this area, this is called wetted area. And we have this distance, which is represent the circumference of the wetted parameter. This is called wetted parameter. Now, the hydraulic radius is the area divided by perimeter, which wetted, and this is wetted. And the S is the slope. The slope, I mean by how much is this sewer and how much is this sewer is there. So the slope of this line, which is usually should it look like to be equal to the slope of the hydraulic line. And then we have Manning is say that the velocity is equal to 1 over n r over 2 over 3 s 1 over 2. And then the q will equal to v times a. Now, which a? Exactly the a that we have it here, and which v is the velocity that's here, then it will give you the q. Now, this q is the real one we have. And by the way, this equation, it's the same that we have here, but this is when we have the r in feet. When you have r in feet, then the q will be in feet cubed per second. And when we have like 1, so if this is in meter, then there will be, will be meter per second. Everything is clear?
Yes, sir.
Okay.
Yes, sir.
Okay. Now what we have it here, we don't want to have a fully flow. I want to have a partial flow. And we have a curve that represents. So because I don't want to every time go back and calculate the area that's here, because it will be somehow time consumed. So there is a curve that represents when we have the flow like this, there will be a Q, and when we have fully flow, there will be a Q, capital Q. So small q over capital Q, it will be it will be this is will relate to the small d over capital D. And again, for the V, the same thing for the velocity. When we have fully flow, there will be a velocity. And when we have half a flow, there will be another flow. So we have a curve. Here is this curve. It will represent the d over d. You can see if d over d is equal to 1, which is 100%, the q there is a this is the discharge that we have. And this is what for n constant, but n variable, because I want to have a constant. Sometimes the source will be in the bottom. It will mean not be like what we have in the top. Sometimes we will there will be a kind of different surface lining from inside. But we should use this one. So we have to go with this this curve. So this curve is representing Q over capital Q. Here's the QD, here's the capital D. In this case, when we have fully flow, there will be capital Q. When we have this partial, we have a small q. So this Q divided by this Q will be founded by having small d over capital D. So let me say if I have d over d1, so you can obviously you can see here's the d over d, and d it will be 1. And if I have half flow, it means that the d over d is equal to 50%, means half of flow. There will be, yeah. So the small q over capital Q is equal to 50%. It means that the flow will be half of the flow, the capacity of. And by the way, this is just for the q. We have also for the velocity. We can say when we have half a flow, look at the velocity. The velocity will be 1 point something, 1.1 greater times the velocity that we have. And so now this is also the same chart, by the way. This is when we have, this is for the velocity, and this chart we have it. This is will represent V is equal to 1 over N R of 2 over 3 S 1 over 2, and the Q is equal to V times A, and A is equal to pi d squared over 4 Now, this is in case of fully flow. So for fully flow, this is just like William-Hazen nomograph, but this is for Manning. When we have discharge, here's the Q, and we have the S, here's the S, Q and S, there will be the velocity, and there will be a diameter. Here's the diameter of the pipes. For example, if you have 200 liters per second, while the Q is equal to 200 liters per second, then if I have the diameter, for example, if I have the slope is 1 over 1,000, so here's 1 over 1,000, and here's the 200. Yeah. So look at this one. This point will give you, look at this line. This line will represent the diameter. The diameter, it means that the diameter of this pipe will have to be 600 millimeters. So this is the diameter of this pipe. And in this point, you can get, what will be the velocity? It will be between 0.5 and 1, which means about, look at these numbers are velocities. The velocity is in meter per second. So what will be the velocity in this case? The velocity, it will be between 5 and it will be between 5 meters per second. So here's how to use this chart. You have to have the flow. You have to go with the S, and after that you will, the intersection of these two lines, you should be, then you have to go parallel in this point, and you can see there is velocities here, 0.5 and 1. Then you have to say, I will make a kind of visual interpolation to see where is it, and then you have to find the diameter of this pipe. That will help you to go. So this is look like what we have it in William-Hazen nomograph, and it's for Manning. So this is the Q is equal to A or pi d square over 4. This is the A divided by n on R2 over 3, which is S over 2, and this R, because it's fully flow, in fully flow, the R is equal to T over 4, so you can find this is the equation. And remember the flow here in liter per second, and here's in meter cubic. It doesn't matter if you want to use it in liter per second or you want to use in cubic meter per second. And here's the Manning, because this is for concrete, by the way. This chart is for concrete, is for n equal to 0.013 neta, nothing else. So this charge only for concrete, n equal to 0.013. For the other materials, we have the same thing, but the same nomograph, but within a different n. Okay, is it to use this, or do you have any question how to use this nomograph, this chart? Huh?
No, sir, I have no questions.
Okay, so it's clear, I think, right?
Yes, sir.
Yes. Now we have. By the way, I modified the PowerPoint that you have it to give you. This is how we have to design any sewers or sewers. So what we have here, first of all, we have to calculate the flow, and then select a diameter of the sewers that we have, and we say that we are, for the sewers, we should start with 200 millimeters, and we have to put the manholes, and we have to check, is that 200 millimeters will be sufficient by the checking the velocity. If it was yes, then it will be the diameter 200. If it was not, you have to change the slope of this line. And this is a simple algorithm that you may need it in the design, even for the project. And you can see here is the velocity should be more than 0.6. Okay, now I want to start with this example. We have example 1. Here's example 1. It says that we have a circular sewer, I mean by concrete. Okay. And this is circular sewers. We have it here. I mean by this one concrete. So in this concrete sewers, we have the flow Q. And by the way, I want you to make, let me say, agree with yourself to use small q and capital Q. This is for use the capital one for fully flow. Use capital V for fully flow. Use small v, small, for not fully, for partial. Use small q for partial. Use small d for partial. Use capital D for full. So imagine that you have a full, it means that it will should be bigger, and partial it will be small. So we have in this pipe we have a flow which is small q, and how do I know that this is not a fully flow? Because it tells me that this is 3/4 full. What that means? So 3/4, it means that
75% full.
yes, very good. So it's 75% full flow. So it means that this is the diameter. This is a diameter, the capital D, and this is the center of the sewer. So the level, here's the level, and it will be the depth of flow. How much it should be? It should be D. So if I want to translate this, it means that D over capital D is equal to 0.75 per 75%, or D over D distance. So it means that this is not fully flow. It means that the sewer can handle more than 200, right? Because it's not fully flow. Now we have the slope of this line, which is the slope is equal to 0.002. So now find the diameter of the sewer and the velocity of the flow. Now you can use directly the equation, and this is in case that you don't want to use any chart. You can use directly the equation, but I want you to try to learn how to use the nomograph. Now, how to find the diameter? To find the diameter, it means that you have to have Q, capital Q, and one of those things, S, for example. And because I will go with this nomograph, here's the nomograph, you will have the discharge, which is the capital Q, and you can have the slope. So using those two things, you can get any point here, and from that point you can get the diameter and the velocity. Here's the velocities, and here is the diameters. Okay, or you can use directly this equation, which is 1 over n, or 2/3 is 1 over 2. So you have to use this one. You have the n, you have to find the r, which means that you have to find where which is called hydraulic radius. If I'm using the equation at the R, you have to say that here's the R, and you have to find the D. There is a capital D, and this is a time-consuming equation and solution. So what I will do, I will just go to this d over d. And remember that I have a curve that will help me to find the fully flow. Here's the, yeah. So for d over d equal to 75% or 0.75, here's 0.8, this is will be 0.7, so this is 0.75. So look at this one, I will use look at this one, I found a relation between the d over d and the capital Q. Here's the, so how much it will be, the value, it will be about, so this use, because I'm using the curve of d, so this value will represent the small q over capital Q, which will be about 0.9 something, 0.92. Am I right?
Yeah.
Yes. So means that the small q over capital Q, and then we have this q is about to be 200 liter per second, right? As it's given to me, q is 200 liter per second. So I can say using the partial flow, then this at d over capital D equal to 0.75, then the small q over capital Q will be about 0.9, 0.91 something, 0.92. Okay, so I can say small q over capital Q is equal to 200 liter per second divided by capital Q. I can say this is a full, and it will be 0.92. Now, how much will be the Q then? Okay. So
217.39.
200 liter per second divided by 0.92, which is B, 200.
And 17.39.
Exactly.
0.39.
0.39. So 39 liter per second. Do we have right now this Q? No, but the capacity of this sewer to hold this flow. Okay. Now this will be the fully Q flow. And we have this slope. The slope of this line is equal to 2.002, right? Which just means 2 per 1,000, right? So I can use these two ones and use it in this diagram to find the diameter. 217, remember that we have 217. Now 217. Where's the 217? Here's the 217. I can use, I will use the yellow one. I will use 200. This is 200. This is 200. 210, 220. It means about, it will be about this. Okay. So this is 270. What else? What else would I have? I have the S, the slope, which is 2 over 1,000. Where's the 1? Here's the 1 over 1,000. This will be the 1 over, will be the 1 over 1,000. 2. Yeah, it will be look like here, right? Because we have 10, yeah. 2 over, yeah, it will be 1 over 1,000. It will be after 1. It will be around here. So we should go with this one. Yeah. Now, remember that we have this. This will be the point that I have. So means what? Means that this sewer will be, look at it will be close to which one? This is the diameter, by the way. These are the diameters. So the diameter of this wall can be said it will be approximately, so the D capital D, the capital D is equal to 600 millimeter. Okay, and what will be the value of the velocity in this part? When we have this, I should look at these two values, and I can say it will be in the half, will be about 0.75 meter per second, because these are meter per second and this is meter per second. So what will be the diameter, the velocity in this pipe? It will be 0.75 meter per second and the diameter will be 600. So for this sewer we can say, so I can say, okay, so the diameter will be 600 millimeters. And the V, which is the V full, velocity at full flow, will be 0.75 meter per second. But remember that we don't have full flow, we have a partial flow. It means that there is something else that will be V over capital V, because V is for the 200 liter per second, the existing one, the V full, which is for 217. Now we have this one. I want to see the velocity when we have this. And then should be founded by having a relation between those two V's. So that means I have to go with the partial flow diagram. Here's the partial flow diagram. You can see, because we have d over d here is equal to 7.5. This is for discharge, and this will be, because this is the curve that will be for V over capital V. And you can see what will be the D? It will be the V over capital V will equal to 1.15. And what is the unit? Without units, because it's a division between v and v. So the velocity that we have in this case will be more than the v full by 1.15. So this one we have 1.15. What means that so at small q, which is equal to 200 liters per second, we will have the velocity is equal to 1.15 times the v full, which is equal to 1.15 times the velocity, which is 0.75 meter per second. And this will be how much?
0.86.
Very good. Meter per second. Now, remember that in case we just have to know that when the D is going to approach to be capital D, just we will have a higher value of flow, but sometimes the velocity will be more higher than the average velocity than if we have a fully flow. So we have for full flow 0.75, but we have this time 0.86. And what is the reason behind this? The reason is that when you have a case of partial flow, the resistance to this flow from this part will be, there will not be any resistance to this flow from at least this top part. So it means that we have a higher velocity than if we have completely flow through the pipe. This is the only, and it will be normal to have a velocity more than the V full, and just for velocity, not for the flow. Is that clear to you, please? It's very important, by the way. You will have in the final exam something like that. You have to be familiar to how to use these charts and the partial flow charts. Okay.
Yes, sir.
Now, okay, we have another example, which is example 2. We have a flow, and the flow here is again, we have a flow, partial flow is equal to 600 liters per second. And this is again when we have a 30/4 full. It means that we have 75, it means that we have the D over capital D is equal to 0.75. Now, I say that we have a Q. Again, this is not, should be capped. This flow, now this is the real one. And this is called full at maximum weather. So this will be wet weather flow, maximum wet weather flow. So we have at maximum wet weather flow, which is the Q is equal to 600 liters per second. There will be D over D is equal to 75%. We have the dry weather flow, and this means the Q dry weather flow is equal to 150 liters per second. Determine the diameter minimum slope. So I want to see how much it will be the diameter and the S of this sewer. So neglect okay, now we should follow the following. Then we have the Q, we have the D. So we said that for D over D, which is equal to 75%, how much it will be the capital Q over Q? The same partial flow curve. So we found that already, right?
Yes, it was around 0.92.
Yeah. I think it was about, yeah, 0.9 something, 0.91, I think, yeah. It will be 0.91. So it will be 0.91 or 92, I don't remember. And the small v over capital V will be how much? And this is will be about 1.15. Now,
Therefore, the Q over Q capital it was 0.90.
90 exactly, or 9 something?
0.92.
92, okay. Now, this is what the Q over capital Q. It asks us to find this one. So what should we do? First of all, we have this Q. We have to find the capital Q or the fully flow. So I can say we have a Q maximum. The Q maximum, it means that the full. Let us not use the maximum, let us use the full, Q full. So the Q full will equal to Q times this one, 0.92, which is equal to 600 liter per second times 0.92, which means, oh, I'm sorry, no, divided by. So 600 liter per second divided by Q full will give you 0.92. So it means that Q full will be equal to how much? 600 divided by 0.92, which means how much?
It's
600.
652.
That's liter.
0.17.
Yeah. So it's liter per second. Now we have this full, and keep in mind this number. Now we have for the minimum Q, this is what will be, it will be 150 liter per second, right? Now we have D over capital D. I don't know how much it will be. Okay, and now we have Q over Q is equal 92, and we have to find the V over capital V is equal to that much. Okay, now we have, this is Q minimum. Q minimum, let me say 150 liter per second divided by, look at this one. This is minimum flow, right? And we have, in this case, the total capacity of this sewer was how much? 652. I want to see, in case that we don't have, we have minimum flow, we said that 75% or 75% of the fullness of this sewer it will be when we have a maximum 600 liters per second. Okay. Now, when we have a lower value of the flow, which is minimum dry weather flow, that's 150. So I will see how much it will be the depth of flow. That's by dividing by the small q over capital Q is equal to how much? 150 divided by 652. That gives you 23%. It will be 0.23. So it means what? It means I can find this is D over D. So I can see I will use D over D when we have D over D, this one, 0.23. Look at this one, because we have minimum, I will have minimum velocity. Assume, and this is, we say that the velocity it will be the self-cleaning sewer. It means that this sewer should need to be cleaned by itself, by the flow, when it should have velocity of how much? How much is the value of the minimum velocity for self-cleaning?
Sir, could you please repeat the 0.23? I didn't
Okay.
get that.
0.6.
This is 0.6 meter per second. Now, your colleague asked, what is that 0.2, 0.3 represent? Now, I will make it clear more. This is the sewer, okay? This is will be 7.35%. This is gonna be maximum weather flow. Or let me say this is in case that I have a 600 liter per second, okay? So what will be the value of the D, this over capital D? How much it will be this one? D over D in this case is equal to 75%. Am I right? Hello?
Sir, yes.
Yes. Now, the second case that I have in this sewer, that I have the same pipe, the same sewer, but it will have lower value of flow. This is what we call it as dry weather flow. Dry means it's not including any rain, right? So the flow here is how much? The flow is equal to 150 liter per second, right? So
Yes.
yeah, the idea is, first of all, I have to find the D over D. Here's D over capital D in this case. In this case, D over D, we have from this relation, I have this Q and I have, and I can find the whole flow. This is will be, let me say, the orange or the green one. When we have the green one, the level of the sewer in this one, this is will be the whole full capacity, which means Q capital. Here's due to this one, due to knowing that the D over D is 75% with this one, and using the partial, I get the Q was equal about 652 liter per second. Am I right? Now go back to this one. Neglect about this part, just you have this value and you have this value. We have the full capacity is 652 and the flow here is 150. Now what will be the D over D? The D over D now is will be 23% or 23%. So the sewer is gonna have lower than the quarter. Okay, so what I need for this value, I need to know how much is, because in this case, I have to keep the velocity at 0.6 meter per second. So I have D over D, I have the velocity here. I can find what within using the same, we can use the same, this one. I can, now I will go back with this one. I will say, but this is 0.2, this is 0.3, this is will be 0.23, and I will get back to find the relation. What is that? Oh, sorry. Yeah, it's inverse. Sorry, 2.3. This is 0.1. This is 0.2. This is 0.3. So 2.3. It will be about this. Let me use the line. It will be better. It will be 0.23. And then there is yeah, go by this one. So how much it will be? It will be about 0.6. I'm sorry because this, yeah, this will be the right one. So at d over d when it's equal to 0.23, what will be the small v over capital V? It will be about how much? 0.6. Okay. Now, I have assumed that the self-cleaning velocity it will be 0.6 meter per second. So what will be the V full? This is V full. The V full is equal to 0.6 meter per second divided by 0.6, which means it will be equal to 1 meter per second. Now, when I have the V full, which is equal to 1 meter per second, back here, this is the case. So in this case, this sewer can hold Q of 652 liter per second, and it has a V full of 1 meter per second. Now, knowing those two values, I can find the other two things, the other two parameters, which are the diameter and the slope. Here's the diameter for 652 and 1 meter per second. First of all, 652. Where's the 600? This is the 600, and this is 1, 2, 3. That will be here. This 652, and this will be the 652. And what will be the d velocity is the velocity. So what I should do? I should go like this. I think we have. Can see? Here's the 600. This is the Q. The Q here is Q is equal to 652 liter per second. This is the full capacity of the pipe. And here's the velocity. Look at the velocities. This is the line of the velocity. Here's the line of it. Now here you should see it will be with which diameter it will give you. This is one of the things that I'm looking for, which is the 750, 900. So I can say then the one. So okay, from this one, here's the diameter of this sewer that will give you the solution. This is one, and then also I can come. What will be the slope? It will be 1 over 800. So from these two ones, I will say that what will be the, I can say then the diameter of the pipe will be 900 millimeters. 900 millimeters is the diameter of the sewer, the required diameter. Now, when I have the D, here's the D, I will go back here because it asked me to find the diameter minimum slope. What will be the minimum slope? The minimum slope, it will be the slope will be 1 over 800. This will be the minimum slope of this sewer. And check with what we have. 1 over 900, it will give us how much? Possibly, or as we mentioned, we have an empirical equation. S minimum should be greater than the 1 over D. The D here is 1 over 900. and actually our S, which 1 over 800 is already greater than 1 over 900. So, okay, I can say this is work. Clear? Any questions?
No, sir.
Okay, so I will give you a briefly notes. First of all, you have to look after these small and capital letters. Small q, it will be represent the flow in current situation. And the capital, it will represent the flow when the sewer is acting as working all its sections. So the V full, it will be when we have over Q cup. The D over D will represent the depth of flow and divided by the diameter of the spore, and it shouldn't be more than 1 ever. And the other thing that we have to have a minimum velocity, and we have to check to use these partial and the chart that we have. Now